Sorry?
Closed shape.
Closed shaped. Well, it should be an area that's bordered by straight lines, straight line segments. And a polygon is simply a sequence of straight lines, segments, where the start point is the same as the end point. Okay, you have to close it, as she said. A convex polygon, on the other hand, is a special type of polygon where if you take any 2 points inside the polygon and join it by a straight line, that entire straight line should stay inside the polygon. Okay, so for instance, here's an example of a convex polygon. This is a convex polygon because I can take any 2 points inside this polygon, and if I join this by a straight line, that entire straight line lies inside the polygon. Now, what's an example of something that's not convex? Anything that's star shaped is an example of something that's not convex. So, for instance, this here is a non-convex polygon. Why is that? If I take a point here, and if I take a point here, if I join them by a straight line, it wanders outside the polygon. Okay? So this here is not convex. This here is convex. Another way to explain this, yeah, come on in, is that these internal angles are all less than 180. Okay, whereas here you'll see that there are some angles that are greater than 180. So whenever you have that, you're going to have some trouble. Okay, now that's not enough because if you have a triangle, in a triangle you never have anything more than 180. So that's fine. I'll take that back. So everyone clear about what a convex polygon is? So you're given a n-vertex polygon. What does n-vertex mean? Meaning these points here, they're called vertices, and there are n such vertices. Okay, you're given a polygon, and then you're told that these polygons are greedy, which means that they are expanding. Okay, and in particular, they're expanding by a distance of d. So there's some expansion factor that happens, and so the polygon grows. And I'll show you a picture of what that means in a couple minutes. And you're also told that this expansion happens a number of times. In fact, you're told that it happens g number of times. Given all three of these, you're asked the question, what is the area of the new polygon, of this expanded polygon? All right. So first of all, we have to know how to compute the area of a polygon, which is a minor challenge. And then this darn thing is growing, and we have to figure out what it means to grow, what is it going to look like after it grows, and what is the new area of this polygon. Okay? Everyone clear about the problem? All right, so here is the picture. You start with this polygon, and then every point that's outside the polygon but within a distance of d will now become part of the expanded polygon. Okay, and here that expansion has happened twice. Okay, so here this distance is d, so it's expanded by d, and that has happened 2 times. So g is equal to 2 here. Is that clear? And d is equal to 1. Just by looking at the grid, you can see that this distance is 1, this distance is 1. So it has expanded by 1 in all directions. And it has happened twice. So question is, how do I find the area of this strange structure?
Perimeter times the side plus the...
Let people think. Hold on a second. You just hold on. So first of all, let's start with a simple case. Let's say that there is no expansion. Let's say I have a polygon. How do I figure out the area of this polygon? Well, in this case, it's kind of nice because it looks like the bottom part is all nice and rectangular. But the polygon I drew here is not so pleasant. So the question is, if I gave you a general polygon, how do I figure out the area of this polygon? Well, what's the simplest polygon that you can get?
A square, a triangle.
A triangle, right? Do we know how to find the area of a triangle first? Yes? What's the area of a triangle? So it's half base into height, right? That's the formula we've seen many times. But then that poses a new challenge. How the heck am I going to find the height of a triangle? So there are lots of challenges, and we have to figure out each one of these. But let's assume that we can figure out the area of a triangle. If I know how to compute the area of a triangle, can I use that to compute the area of a polygon? That's one of the questions we have to think about, and it turns out that that is easy. Let me postpone that for discussion for you. But what we're going to do now is to say, all right, I could potentially find the area of the polygon, let's say, and we'll go through the details in a bit. But then what is this expansion business? What's going on, right? So how should we think about the expansion process?
Ratio?
Sorry?
Like everything expands in the same ratio?
Ratio-wise?
Yeah.
But if I want to apply ratio, you're saying I should just multiply the area by some constant factor. That's what you're thinking, right? Not sure if that'll work for you. Yeah.
Why don't you like double the distance? It would be like proportional to the square or something like that.
Well, so we don't know whether a double expansion increases by the square. We don't know that.
So for each side, we have to add the distance d, and for like if there will be like n sides, there will be added distance of n. So the new size will be like the size plus d. And then
So that's a good thought. What he's suggesting is, let's figure out the area of the strip around that polygon. Let's assume that we first go and figure out the area of the polygon separately, and then we'll focus on the strip around it and figure out the area of this. But that looks like a strange thing, and so we have to kind of figure out how we're going to approach that. Yeah?
You can divide the area into rectangles and circular segments.
Okay, all right. Stop right there. Yeah.
And the corner is a segment.
I know. I got it. I know you know. So our job is to be able to characterize this strip in order to figure out how the area is expanded. And for this, as Rukman said, we're going to, what's going on here? We're going to use something called Minkowski Sums. I gave the name not to impress you, but more so that you can go and find this on the web somewhere. There's a ton of literature on it, but it's not easy. It's kind of it's a very complex topic. But I'm just mentioning that because then you can go and find code for Minkowski sums in a reasonably easy manner. Now, what is a Minkowski sum? Well, let's focus on what we are given. If you look at this example, let's say we have a strange looking polygon here. This here is the first Minkowski sum. In fact, it's a Minkowski sum between the polygon and a and a circle. And the way this happens is the way it's described, the way Minkowski described this back in, I don't know, 100 years ago, is that you take a ball and you center it on the polygon and you make it walk along the border of the polygon. Whatever it touches, that's my expansion. Okay? Which really is the same as the way the problem was described, because it said that anything that's at a distance of d from the polygon is all going to be part of the expansion. All right? Now, the important thing to understand here is that somewhere here, the circle, things are not straight lines there where it turns. And that's because the ball comes in there and starts to travel in a different direction, right? And there, you're going to get some circular arcs. So if you take this ball and if you move it down, you're going to get a straight line at the edge, right? All this will get covered. And then when it comes here, it'll start to turn. And right at the place where it turns, it's going to leave this impression here, and then it's going to roll that way. Okay? So it is going to leave a piece of a circle where it starts to turn. Is this starting to make sense? You were going to say something? Okay. So this is called a Minkowski sum between this polygon and this circle. Okay, just for you to know. Yeah.
So does the Minkowski sum build on top of itself, or is it sort of like our sample problem where you start off with just the convex polygon and then sort of like a big circle? Or does the Minkowski sum do the next step iteration with?
Well, this is just a mathematical definition that says if you give me two objects, then in order to figure out the Minkowski sum, I'm going to roll one of them, or actually slide one of them along the edge of the other one. Actually, Minkowski sum is a little bit different because the whole circle needs to sit here. Here the center is on the polygon. So there's some slight difference, but that's okay. With a minor change, it turns out that these two are roughly the same. But Minkowski sum doesn't care about expansion and twice expansion and all that stuff is simply not relevant to Minkowski sum. All it says is, give me two shapes and I'll compute what happens when you slide one of them around the other. In fact, this doesn't even have to be a circle. It could even be a triangle. And look at what happens when you have a triangle. Yes?
So does the Minkowski sum give the area for any arbitrary?
No, it doesn't give any area. It tells you how to compute that region. Then finding the area is a slightly different problem. Okay, and we'll talk about that in a few minutes. So so let's say I take this. Let's say I do that. And I ask you, what is the Minkowski sum between this and a triangle? All right, let's say I have a triangle that sits like this. This is my triangle. What do you think the Minkowski sum is going to look like? Well, you're going to roll, or you're going to slide this triangle, and as it slides, it's going to look like that, right? What happens at the end? Our inclination is to turn it. That's not how it goes. Instead, it has to face in the same direction. Okay? So what happens is that it comes and sits like that, and then starts to slide in that direction. Okay? And then it'll go all the way up to there, and then when it comes to this part, something strange happens. It can either slide along that, it depends on some angles and stuff, which I'm not going to get into unnecessary detail right now, but it'll start to slide that way, and then it'll come over here, and then in fact it will go further up at some strange angle and become like that, and then it will start to slide down. So the Minkowski sum is going to look a little strange, but Minkowski kind of defined how this can be computed. Now, of course, if it is a circle, it turns out to be a lot easier. Yes, Demba?
And it works for all shapes, right?
It works for all shapes. I can put in a polygon. I can take two strange-looking polygons and do this. Okay. Now the code for that starts to get complicated, as you can imagine, right? We won't do that here. But what I wanted you to understand was that there is a foundational theory under all of this, and it basically uses that. Now, the next thing is we don't need Minkowski sum in order to figure out the solution, because it's a lot simpler with a circle. When it's a circle, as the circle moves along the straight line edge of the polygon, the edge of the circle is just going to do a straight line, right? Because it doesn't go up or down. None of those curves show up. So there's a part of it that's simply going to be a circle, going to be a straight line. And in fact, I have an example. I have something here. If you take the circle and if you move it along that edge, you'll see that the straight line part is exactly that purple part, which is the same as one of the sides of the polygon moved out. Okay. What else do you see? Here is what else we see. If we draw circles at each of these vertices, and if we draw something called a tangent to these two circles, then you'll get the outer shape. So you get this, then you can draw another circle here and draw the outer tangent. Remember, what's a tangent? It touches these two circles at exactly one point. Same thing over there, same thing over there. So now you only get this purple patch that's going to be a nice rectangle whose width you know because that's the same as the polygon side, whose height you know because that's the distance by which it expanded, right? The d, right? And so it's very easy to compute the area of this rectangle. So similarly, I can figure out the area of these rectangles on the side. All we are left with is what happens at the vertices. And what we saw is that at the vertex, we have a circular arc. Okay? Sorry? Which is a sector in this case. That's right. So the sector now is what we have to figure out. And so what happens is that if we know the area of this polygon, the area of the expanded strip is simply a bunch of rectangles and circular sectors. Okay? And that's what Rukman was saying earlier. But I just wanted to make sure everyone is with me on this. Yeah? Okay, so what's an area of a sector? So it all comes from the area of a circle, right? So here's something from the web, quite easy. Area of the regular circle is pi times r squared. But that's because the entire angle that you're turning is 2 pi. If you take some other angle, theta, then the area of the sector is just theta divided by 360 or 2 pi or whatever your full circle angle is, times the pi r squared. Another way, if you're given theta in radians, it's simply theta over 2 times r squared. Very simple. So all you need to know is r squared. In our case, r is the same as d. Well, if you're doing the expansion twice, it'll be 2d. Otherwise, it'll just be d. right? So therefore, those circular parts that we saw here is quite easy to figure out. So all of this is easy to figure out because they're just parts of a circular sector. And the straight lines are simply rectangles. And so we just add all of these up. Yeah?
Even for the second iteration, does this hold? Like
Yeah. Well, we're not going to do a second iteration. Instead, we'll just assume that we expanded by 2D.
are they equivalent?
They are equivalent. Yes, they are. Because think about it. If something is at distance d from the, let's see, let me see how to explain this.
The angle is not changing, only the distance.
No, it's something much more intricate. What we're saying is if I take any point here, it's at distance d from some point there, right? If I take any point here, it's at distance d from some point here, which in turn is at distance d from some point there. And so therefore, all these must be within 2D of the start point. That's it. That's all I need. Right? So it's enough for me to just expand by 2D and I'll be done. Is that clear? So that leaves me with, so I now know how to compute the area of a sector. I know how to compute the area of those strips. I know how to compute the area of all that expansion. All I'm left with now is to figure out the area of the polygon, and then I'll be done. Right? Are we good with this? Okay, so area of polygon. For area of polygon, we have to start with area of a triangle. We talked about it. And for area of triangle, somebody told me the formula is half base times height. Unfortunately, in this case, you're given the coordinates of A, B, and C, which could be anywhere, could be turned in any direction. And we have to figure out the base and height of this. Fortunately, there are many other formulas for area of a triangle, which you can use. In particular, I can write the formula for this angle beta here as something like that, and write down the perimeter s squared in terms of A, B, and C and that beta angle, and then write down the area in terms of this s. I know it looks complicated, but if it's given to you, it's there. All you have to do is to plug it in. Writing code for this is child's play, right? Easy. So once we figure out the area of a triangle, which if I'm given the 3 coordinates, I can figure out this length, and this length. Then I can use the first formula to figure out this angle. Then I can plug it into formula number 2 and compute s. Then I can plug it into the third formula and figure out the area. Right? Now, in order to figure out the area of a polygon, it's very simple. Let me redraw it here. Let's say I am doing a polygon. Here's my polygon, and I have all these vertices: A1, A2, A3, A4, A5. Let's just call it AN. What I'm going to do is I will start somewhere. Let's say I start at A1, and I'll take its 2 neighbors and join them by an edge. This here is a triangle. So now I have A1, A2, and AN. I can use the formula up there to figure out the area of this triangle. What have I done? I have now figured out the area of a piece of this polygon. If I remove it, what do I get?
A minus.
A polygon with 1 less vertex. Right? So now I do this again. I find any vertex I like, it doesn't matter which one. And let's say I pick this guy here. I join its 2 neighbors, take this triangle, figure out its area, and remove it. Then I do that with the next one, takes care of that. Keep doing this until there's nothing left, and I would have, all I have to do is to add up all the areas of these polygons, and I would have the, area of the triangles, and I would have the area of the polygon.
I had a question from online. They were asking, like, what do we need beta if the perimeter can just be calculated with Euclidean distance?
You're right. Yeah, he's absolutely right. You don't need beta. Why is that second formula even there? I'm not sure. I stole it from some other location and I didn't think it through. But yeah, S is simply A plus B plus C. Absolutely right. So it's even simpler. You just plug it in here and you're done.
So how many times do I have to segregate the polygon? Is it like
You tell me.
n-2?
Every time I do this, I remove one vertex,
Yeah.
and I keep doing this until I'm left with only 3 vertices. So I'll do it n-2 times. So n-2 triangle area computations. Simply plug it into the formula and you're done. The only problem here is precision. You have to kind of worry about this because it's annoying. Square root 3 over 4 can, actually I wrote that wrong. It should be square root 3 divided by 4, not square root of 3 over 4. I'm sorry about that. Oh no, maybe that is correct. Square root 3. Yeah, you're right. Okay. Okay, we'd have to check the formula. But there is some formula. Go look up some book and plug it in. Yeah. It's not a complicated formula. You can. In either case, it just changes the code a little bit. Okay. So this tells you how to do this. By the way, can you write code for this? Very simple. Start with 1. Find that triangle. Remove 1. Then take 2. Take this triangle. Remove 2. Then go to 3 and do exactly the same. Keep doing this until you have only 3 things left. All right? So it's a simple for loop, and you can figure out the area of the polygon. So we have all the pieces now. And you should be able to go and write code for this. Start with the area of the polygon. Then look at how much you're expanding. The strip of the expansion consists of rectangles plus circular sectors. Figure out the area of each of those pieces, add them up, and you're done. Okay? Is this the one you tried?
No, I tried parenting gas.
Different one, okay. This is the one of the problems you guys solved? Okay. Did you solve it differently?
No, same exact way. Just took some code and calculated the area of the polygon. Everything else was easy.
Yeah. Yeah, you can find, by the way, when you go to competitions, you take a bunch of printed code with you, and you can find code for area of convex polygons. Yeah.
There was one thing, so they're not, the vertices are not numbered.
Oh yes, so that's right. I did notice that. So yeah, there is one little confusion there. They tell you that the vertices of the polygon are not given to you in any order. So how do we handle this? If you don't know the order of the polygon, then things don't work out very well, because when I start to remove this vertex, I don't know what its 2 neighbors are.
Find the center. It's a convex.
Relax, hold on. Let people think this through.
You want to question?
I know I did. Any thoughts on this? So it turns out you're given these vertices, but not in any particular order, right? That's the problem. If you take those points and run something called the convex hull algorithm, you can easily figure this out. So there is something called convex hull algorithm, which essentially takes all the points and finds the convex polygon that contains all the points. Since these points are already sitting on a convex polygon, it should give you the right answer, right? That's one way. Another way to do this is to actually think about the convex hull code, which works as follows. You start with, let's say you start with the vertex with the highest y coordinate. Okay, and then think of the x-axis running through that point. You then take, after this it's actually quite simple. You find the angle of each of these, let me find a different color. Then join A1 to each of the other points. Remember, you don't have it in any particular order, right? And then find the angle between these lines and the x-axis. Oh, one more. After you find those angles, sort them. And the order in which they'll appear is going to give you your order of the points. Okay. Another way to do it is, as Rukman suggested, namely take all these points and find their average point. The average point, the mean point, is going to be, it's called the centroid. It'll sit somewhere there. Just take their x coordinates, find the average. Take the y coordinates, find the average. Okay. Once you find a point in here, then you can do the same trick and join this guy to each of these other points. And again, find the angles of each of those line segments and sort them. It'll put it in that order, and now you know which ones, what the ordering of the vertices are. But
Use the centroid to catch up the area, right?
that's true. You can directly do that as well. Yeah. But you still have to find the order.
You don't need the order.
You do.
Oh, okay. You still need. Okay.
Yeah. So we still haven't talked about how to find that angle. So let's say I have A1, and let's say I have one of the points. So let's say A4, and I have the x-axis here. How do I find this angle? Sorry?
Use an inverse trig function.
Inverse trig will work, but with what values?
You drop a perpendicular line from A4 to the x-axis.
Okay, I drop that, and then
The distance to the x-axis.
what is the length of this?
Delta y, right?
The distance. No, that is the. What would that be?
Delta y, delta
So it's the difference in the y coordinates of A1 and A4, right? So it's y1 minus y4. So let's say this point is x1, y1. Let's say this point is x4, y4. So therefore, if you take the absolute value of y1 minus y4, that's this length. You can also find the length of this guy here, which is the difference in the x coordinates, right? So that's going to be difference between x1 and x4 absolute value. That's the horizontal part. So now you have the angle because tangent of alpha is y1 minus y4 absolute value divided by x1 minus x4, and so alpha is tan inverse of whatever that ratio is. Is that clear? So that's how you find that angle, and then you take those angles and you sort them, and that's how you figure out the ordering of the points. Is that clear? So lots of little pieces in this problem, but once you put them all together, it should be clear how you solve the problem. Questions? Yeah, thank you for reminding me that there was that little annoying part to this. Okay, I strongly recommend that the next mock competition will give you this problem. Please try and get all the pieces together and write the code for it. Okay, shouldn't be that difficult. But it's unclear if you'll be able to submit solutions next week, right?
It's a little unclear. I believe so. Like
Yeah.
in the past, it only takes like 4 days.
3-4 days, yeah. Okay. If we don't have it this weekend, it'll be the following weekend for sure. Yeah.
Okay,
Huh?
so you're saying that the mock competition will have the problem.
We'll have this particular problem,
And also the
so
other
that
problem.
you can take whatever you learned from this lecture and actually turn it into serious code that works. Right? How many of you don't think you can do it? Not sure? What's sorry?
I don't think my coding skills are good enough.
It'll take time, but you're still not sure you can do it. If time is not the issue.
Time's not the issue, yeah.
Yeah, that's what I thought. You?
I'm still a beginner. I don't think my code will work.
Are all the pieces in your head?
Yeah.
Okay, then you can do it. That's what you need to believe, yeah? And then there are people here who can help you. So make sure during the competition that you're on Discord and feel free to ask questions. There's nothing wrong with that. This competition is not meant for you to be competing against each other, but to learn from each other. So feel free to say, hey, I'm stuck here. Any thoughts, any ideas, any hints? And somebody will hopefully respond to it. Because that's the best way for you to learn from each other. Sorry?
Is there any way to grab the tan inverse in the particular code or something?
Well,
Tan inverse.
ATAN, yeah.
That's
the standard library.
Yeah.
So you can use the standard library, or you could potentially just leave it as tan and then realize that tan, huh?
It's monotonic.
It's monotonic, yeah. So it's positive in right, yeah. So if you know a little bit more, then you can leave it with tan and figure things out. Okay, all right. Let's move on to a second problem. Questions? All right. Okay, so this is called pandemic shopping. Well, actually, let me finish the piano lessons first, and then we can come back to this. Piano lessons, I'm not going to go through the whole thing, so I'm going to tell you a little bit more. Anybody tried this?
Yes.
You did try it?
Yeah.
You read it, at least, right? So can you explain the problem to us?
Yes. There is a teacher. Piano
Yes,
teacher.
Mrs. Mackenzie.
Very, very nice. She has limited slots time for
Right.
her
Yes.
And because she's very good, a lot of students want to learn from her, and you get the number of slots that she can teach, like available. When you get the number of students that want to be a student,
Sign up, yeah.
sign up, and the hours that they can come. So you need to take all those students and to fill the schedule up and to say how many students you can teach the following week.
Yeah.
The week, and that's it.
Okay, thank you, thank you. All right, so as Nawaz said, this is the problem describes Mrs. Mackenzie, who is a fabulous teacher, and she only has M slots, and she only gives private lessons. So only one student at a time, and students go and sign up. However, they don't directly sign up for specific slots. Instead, they say, "Oh yeah, I'm free from 3 to 4, from 5 to 6, and from 8 to 9." Okay, and then so they pick different slots where they are free from the teacher's possible slots, and then your job is to figure out which slot is going to be is to figure out how many students the Mrs. Mackenzie can train, and what's the maximum number of students she can train. Okay. All right. Any thoughts on this? So yeah, it turns out that this whole this problem has got to do with how to model it properly. Once you've done that, it's just a matter of figuring out what piece of code to use. Okay, I'm not saying it's easy. All I'm saying is you would know what algorithm to use. All right, so how do we model this? Yeah.
I can try my approach, but
Yeah, go ahead and tell me.
the
Yeah.
code part.
Yeah.
I imagine it as buckets.
Uh-huh.
So every student has, let's say, a time slot that is available. So let's say we have a student with the
So the buckets are the slots?
Yes.
Buckets are the time slots.
Yes, and the students
Fall into different-
Yes, let's say that I'm a student, so now
You may be in several buckets.
Yes.
Right.
And then I'll search the bucket with the least number of students.
Uh-huh.
And let's say I have a bucket with one student.
Yeah.
So this student will be.
There's no one else competing for that slot,
Right.
so it's easy.
And
Yeah.
I'll erase his name from the other buckets.
Right.
So then I'll just.
Okay. Yeah. So that approach is sort of a greedy approach. Unfortunately, it's not going to work out in more complex cases. So it's a good start to imagine this. It turns out that the whole thing needs to be cast as a graph problem. Okay, and if you've not had graph and graph algorithms, you're excused for not knowing how to approach this. You're going to say something? No. Okay. So we want to. So what does it mean to cast it as a graph problem? Well, it's to draw a picture that looks like this. Instead of drawing buckets, you're better off doing something like this, where on this side we have we have students, and on this side we have Mackenzie's time slots for training. And we have an arrow that says, oh yeah, this student is free at this slot and in this slot. Okay, this student is only free in this slot, or can take this slot, and so on and so forth. All right. It turns out this is called the maximum bipartite matching problem. It's called bipartite because there are two partitions, and the edges only go from this side to this side. You never see edges on this side, or you never see edges connecting these guys. That's why it's called a bipartite graph. It's called a matching problem because you're trying to match students with time slots. Here is a possible matching. If you look at the green edges here, it gives you a bipartite matching. So you're matching this person with this slot, this one with this one, and so on and so forth. And you want the maximum matching, which means you want to maximize the number of people matched with time slots. Once you know this much, it's now easy because you just go and find the code for maximum bipartite matching. I will discuss this later once we are more familiar with graphs, but I just wanted to say this much so that you know where to look for the solution. You're going to say something?
Cover graphs.
Yeah. I'm still. Graphs will come next in class, and at that time I'll start to also have Ricky push more graph problems for you in the mock competitions as well. But at that time I can discuss the algorithm for this. It uses something called, well, it uses breadth first search, which is straightforward, but it also uses something called path augmentation. You can figure out whether this here is the best possible. And here it's kind of obvious because one of the students has picked no slots. So clearly you cannot match that student with any time slot, and all the others have a time slot. So you're done. This one is the best possible. But it turns out that there is, even if that student had some possible connections, let's say that this student only connected to things that for which you already have the green edges, right? It turns out that there is a way to check whether you can go from 5 to 6. And that's using something called a path augmentation. We'll talk about this later when we get to it, but for now, feel free to find code for maximum bipartite matching, plug it in, and it should work. Okay? Any questions? Everyone understand these terms? Maximum because you want to maximize the number of students you're matching. Bipartite because you have two sets that you're trying to match. So these are useful, for instance, if you have people and skills, things like that. So people and jobs, residents and hospitals. In fact, they use similar things for various algorithms in real life. Okay. Questions? Okay, I think I don't have anything else. Oh, wait, this is wrong. All right, are we ready for the third problem for the day? How am I doing with time? Okay, I have 20 minutes. Perfect. Pandemic shopping.
That sounds familiar.
Pandemic shopping is staying home and not doing anything.
For Amazon?
Yeah, but this is not Amazon shopping, it turns out. So let's find out. Okay. Yeah, I don't know why it's called pandemic shopping because it seems to have nothing to do with how you should behave during pandemics. Here is a link to the problem in case you want to go find it. It's called pandemic shopping. Here's what the problem is. You're told that there is a physical store. So there you go. Nothing to do with the pandemic. The store is rectangular in shape, okay? And you're told that there is an entrance and exit. There's at the southwest corner there's an entrance, northeast corner there's an exit. And you're told that there are two aisles, and these two aisles are we'll call them as A and B, which are in either end of this area. And finally, there are also product aisles. So there are various product aisles. I should show you this picture. Ignore the arrows and the green stuff for now, but those two are your north-south aisles. Come on. Where did it go? Something happened to my slides. Okay. So this here is A, this here is B. Those are your two north-south aisles. These are your product aisles, like in any grocery store, right? And these product aisles are numbered 1, 2, 3, 4, 5 up to n. Okay, so this looks like a regular grocery store, nothing strange so far. But what they want to do is the following. This is where pandemic shopping might be. So now you're putting me on a leash here.
Just noticed?
So what we want to do is to have people come in through the entrance and leave out of the exit. Okay, and we'll give them directions. There'll be marked arrows on the aisles. And essentially, we're trying to herd them so that they don't go around wandering all over the place. We want them to come in through here and not get lost within the store. We want to have them come out, but we also want to make sure that they go visit all the aisles and spend as much money as possible. All right? So our job, or the job of the manager, is to put arrows on each of the aisles in such a way that all the aisles are visited, either in this direction or in this direction. Well, they complicate the problem a little bit by saying that someone already drew some of the arrows. Your job is to finish the work and put in the rest of the arrows so that people can go and essentially do the job, namely visit each of the aisles and please get out of the store eventually. Right? We don't want the arrows to be in such a way that they just simply keep running around and get lost. Does that make sense? Well, that's not the end of the problem. What you're asked is, you're given a floor plan and the arrows on some of the aisles. Your job is to not only mark the unmarked aisles so that the customers can enter from entrance, visit all the aisles, and leave from the exit. But what they really want, the output, is the number of ways that the customer can finish their task, which is kind of crazy, but this is the problem that's asked. Sorry, it's not the number of ways they can make the path. It's the number of ways to. Did I get that right? Is that what they asked? Is it number?
Taking the number of the arrows, like the directions.
Uh-huh. Okay.
Number of unique ways to actually.
Okay. All right. Yeah. Okay. Is the problem clear? So let's go back to this. Where is the? Yeah. So if these red arrows correspond to things that have already been marked, your job is to finish marking all the aisles so that eventually the customer can finish their shopping and leave. And over here, it should be pretty easy, right? What would you do to aisle 1? Go this way, then 2 that way, 3 this way, 4 that way, and then out from 5, right? Now, how many different ways can you label the aisles? Well, there's clearly one, but is there more than one?
Can you use the stable point?
You can use same one more than once, yes. You were saying what?
Do we use those errors or change?
The ones that are marked, they have to stay.
Ah,
You can't mess around with those.
How many are already marked?
You're not, well, in this case, 4 are marked, but it could be different. It could be different problems, could have different markings. So, how many different ways to label the aisles? You see more than one? If not, why? And if so, tell me how you're going to label it. You have one? Okay, tell me. What do I do for one? For aisle 1, what do I do?
left.
Oh, you're going this way.
Yeah, this way, and then you go up to the 5th.
So I'm going up to the 5th, and then,
Oh, wait a minute.
but then I can't come down this way.
Yeah, so
Take it back.
1 is right, 3 is right.
Yeah.
What is that?
Yeah, but that's the first one that we already proposed. Is there another one?
4 is right.
Oh, you're flipping 3 and 4? Is that what you're saying?
Yeah.
If I flip 3 and 4, so 3 is now going this way and 4 is going that way. Is that going to work? Sorry? Then you can never go to 2 again because this aisle doesn't work anymore. You can't go down. So there's only one way. Is that clear? Because this right aisle, you can't come down on it. Okay? So in this particular case, there's only one marking, one set of markings that's going to work for you. Is that clear? So you're asked this general question about how to deal with any situation. How do we approach this problem? So you guys solved this problem?
No.
You did not?
I didn't get enough time.
Okay, yeah.
Yeah, because the general problem is tougher.
Sorry?
Because it's a general problem, it's tougher.
So if both of the side arms are going up,
Yeah,
you can't ever go back down. So
that's right. Because they're both going up, there's no question of coming back, which means you have to do 1, then 2, then 3, then 4, then 5. And if you're going to do 1, you have to do 2 the other way, and then 3 has to go the other way. So that means you're left with only one way to do it, right? Is that clear? But what if,
no, but the original problem says travel to John.
correct. Yeah, if you want. Yeah, but even if, even with that rule, I can't mess around with the direction for 1. If the direction for 1 goes this way, then I can't start with 1 and I'm stuck. And because the arrow on the right aisle B is only going up, not coming down, I can't come back and pick up 1 later on. So whatever products are in aisle 1, I'll never be able to get to it. And that's not acceptable. So therefore, that's not a solution we can count. Right? So that leaves us with, well, how do we solve the general problem?
I guess what Ian said is one case when they're both up, it's only one ever.
Yeah,
At most one. Maybe they give you a wrong valid one.
yeah.
But what if the left goes up, the right goes down, you make some sort of loop,
Yeah.
and then you get
Yeah, so what if they had flipped this arrow? How do you work this out? Is it going to work? Will the customer ever get out?
Yeah, if the first sentence that was,
Sorry?
if the first sentence that was the way right here, then they'll always find the path to the exit.
If I didn't catch this sentence.
Sorry, if the left arrow and the fifth arrow are the way in this diagram, and you flip the right arrow.
Yeah, all other arrows are the same. If I flip this one, now can you answer the question?
Yeah, they'll always exit.
How are you going to orient the other aisles? Which way would they go?
They can change it.
Oh, really? Are you sure? I'm not so sure. Sorry?
once we make a complete loop, then it doesn't matter how others are oriented. Is that
Uh-huh.
maybe a bigger loop? If you have a bigger loop, everything inside doesn't matter.
Hold on, hold on. Think it through. Let me hear from the others.
If we go from forward, if you go from right to left, then you go to third one from left to right, and second one right to left, and fourth one left to right, and then again you go to fifth, and you can get out.
So remember, let me just draw this picture before I take your comment. So this is what it looks like. I got this guy going up, that guy going down, and I don't have 1, then 2 goes right to left, and 5 goes left to right. And I still need to do 3 and 4. Yes, Demba, you're saying?
So I just have one clarification if I may come in.
Yeah.
So in that case, right, if you do choose to go right one, you can never go up because the direction is facing
That's right.
up.
You're going to be stuck. You have to stay in the store forever.
Can you go up, 3, down,
Uh-huh.
1?
You
go
could.
Up, 3,
Yeah,
2.
you can do whatever you want, but you have to visit all the aisles.
Yeah.
Okay, so tell me what is your strategy?
So from
How are you going to orient these guys?
So from entrance, you go up to 3.
No, tell me the orientations of 1, 3, and 4.
Oh, 1 is this way, 3 is that way.
You want 3 going this way,
Yeah.
4,
4 also that way,
and 1?
and 1 is going this way, left. Yeah.
Oh.
Right.
If 1 is this way, then it doesn't matter which way 4 and 3 are. Once you have a bigger loop, you can be anywhere on the loop. Right?
You're right. Yeah.
So then it doesn't matter where 4 and 3.
Yeah. So, but you didn't have a choice on 1, right?
So essentially,
Yes
you're
or no?
saying that
You don't have a choice on 1. Is
yeah,
that
you don't have a choice on 1.
correct?
If the arrows are on the opposite sides, but once you fix on 1, everything else is twice. Like you have 2 choices. So 2 power number of edges.
We do have choice
Okay.
We use 2 to get
No, it's not 2 to the end. Sorry?
We do have a choice on 1.
You do have a choice on 1. How's that? We just said that if we had oriented it this way, then I can. If I start going this way, I'm dead. I have to camp out here forever.
I see.
Yeah.
Isn't 2 power 3 edges?
But I mean, you only ever have like 0, 1, or 2 choices, right?
In this case, but in a more general setting, I don't know how many are marked prior to are given as the input.
And if either one of the north-south aisles are down, then there's a cycle, and you.
Yeah, I mean, there are all sorts of situations. So this is why my next slide says, in order to solve this problem, oh, sorry, I shouldn't be showing you that. There are many cases, even with A and B, because we looked at the case when both went up. We looked at the case when 1 went up and 1 went down. Why didn't you guys look at the case when this side goes down and this side goes up? Or the other case when both are going down?
If both are going down, that's not valid.
Valid. What does that valid mean? So what is your... If both are going down, the answer is 0.
Yeah.
It's the number of ways to orient in such a way that you satisfy the customer, right? That's clear. Good. But what if I had this one going down and that one going up?
So it's all about creating the bigger loop, right?
I don't understand bigger loop. I don't know what that means.
The bigger loop is the like the first aisle and the last aisle, along with the ones along with A and B should fall in form a loop.
Well, so actually, let's go back to the previous case, just to make things clear for you. The previous case, you had this guy going up, this guy going down, right? And we were asking how many different ways to orient the edges. And actually, I never answered that question, so let me go through that. So one thing was clear, one has to be going this way. That's pretty clear. Two was already going here, no choice there. What do we do with three? Well, clearly, if it's going this way, it all works, right? Because I can go start from here, go to 3, then do 1, then go to 3, go and do 2, then 4, and then come back here, and then 2, and then 5 will take me out, right? That's the only. That's roughly the only way I can do it. But then I could have also flipped these, yeah. But you were saying I could flip. I could do any of the possible combinations, and that's where I have a problem with. So, what if I had that? Will this work?
Yes.
So I could do 4, and then 1, 2, 3, and then
once
5.
you're on the bigger loop, you can go to any aisle, right? Like the largest loop, you can go to any aisle, and the direction doesn't
Either
matter.
from the left or
Yeah, you can go from the left or the right. So that's why it's 2 power number of free aisles.
Okay.
And then twice.
Well,
power-
it's not 2 to the number of aisles, because one of them has to face in this direction.
No, even if 4 is the other way.
Oh, even if 4 is the other way?
I mean, of course, 1 should definitely be fixed, but it's 2 power number of free aisles minus 1.
Okay, so you're saying even this would have worked, because then I
Yeah.
would just do with 5.
Yeah, you can go
Okay,
can be
yeah,
anywhere.
yeah,
So
all right.
again, twice because you have. the
Fair
other
enough.
one.
Yeah, you're right. So what that means is these two can go either way. Doesn't matter which one is which, but this one needed to go in this direction. And then we worked this all with 5. What if this were 29 or 433? What are you going to do? So the question is, how do we handle a more general problem
So-
of this kind?
As you said, there are 3 cases, right, for A and B.
There are 4 cases. There are
mean-
many more cases. In fact, yeah, look at this. A and B pointing north, A and B pointing south, A and B marked, one pointing north, one pointing south. A is marked north, but B is not. A is marked south, but B is not. B is marked, but not A.
Yeah, but-
Yeah, these are all different cases.
So what I'm saying is.
I'm telling you how many cases there are for A and B.
This is-
And if A and B are not marked.
no,
So.
but what I'm trying to say is,
Uh-huh.
first forgetting about whether it's marked or not, there are 4 cases. Among them, one case is invalid, right? Then we can consider the marking, and then we can filter out the cases further, right?
Well, sort of, yeah.
Also,
y-
if we have like number 4 in this direction, then the number 3 can be any direction. It's not only the maximum limits.
That's correct, yeah.
Depends on the
So there's 2 times 2 is the right answer for this, 4.
No, he.
I'm saying suppose 4 is going to that direction,
Yeah.
then only 3 can have two choices. Right?
Oh, if 4 was already given to you, you mean?
Yeah.
Okay, yeah, of course.
No, but once you, if A and B are in the opposite direction, the first and last aisle are fixed, right? You can't change them. Otherwise, you can't travel.
No, but
This is,
but nobody told you that they were part of the givens.
That's what I.
No, I'm saying even if they are not given, their direction is fixed. Because if you have to go through aisle 5, it should be in direction only. You can't be going you can't have it in the opposite direction because you can't traverse through it.
That's correct.
Yeah, that's why you will always have either
Oh,
the
this is
bigger-
what you meant by the big loop, okay.
Yeah, that's what I mean, the big loop. Okay.
One thing I guess we're assuming is in the actual problem I remember is both are exit and entrances, the top left and the top
You mean
right.
one could be the exit and the
Yeah.
you could flip. This is what you're saying.
Yeah, you can flip them.
But for that, I mean, that's a minor detail
But then
because
again,
hold on, Rukman. That's a minor detail because you can just flip the whole problem.
Solve it that way.
Yeah,
yeah, there is symmetry,
yeah.
rotational.
So there are lots of issues in terms of all these cases, and you do have to code for them, unfortunately. And so I think it makes sense not to pick this problem because it would have just taken a lot of time as far as I can see. And then on top of it, you have to kind of worry about what happens. What if there are n, and this were not number 2, this were somewhere in the middle, right? What if you could have various choices in terms of how the various aisles are directed, and there are different cases depending on how many of these aisles are marked: 0, 1, 2, or more. Okay, and in each of these cases, you have to kind of figure out whether you can find a path or not. So that makes this problem a little annoying, but I wanted you to see how one could think through these steps. At this point, I don't see a way around just trying all these possible cases, but I'll think about this more and see if there's a better way around this problem. Okay. Yeah, and there are also many cases with product aisles. So somehow I think that if 2 or more are marked, then things are